Hello students, myself Professor Jayesh Prajapati. Today our topic is a three-phase inverter or a six-step inverter. Let us start. Today the question for a day is how to obtain a three-phase AC supply from a DC supply. We already know that the DC supply waveform is like this, and we have to convert this DC supply into a three-phase sinusoidal AC supply. That is a waveform for three-phase AC supply. The three-phase AC supply having a three-phase, that is R phase, Y phase and B phase. These three phases are 120-degree phase shift with each others. That is a three-phase sinusoidal AC supply. Now we have to convert this DC supply into a three-phase AC supply. So the solution for the question is a three-phase inverter. A three-phase inverter is a device that can be used to convert this DC supply into a three-phase sinusoidal AC supply. In this today's session, we will discuss this three-phase inverter. Okay, let us start with a classification of inverter. Classification of inverter. Inverters basically can be classified in two ways. First, according to the output waveforms, and second, according to the types of load. According to the output waveform means whatever the waveform is come at the output, it can be classified in three manners. First, that is a square wave inverter. Second, that is a modified sine wave inverter. Modified sine wave means what? A quasi-square or a PWM wave, that is a modified sine wave inverters. Then sine wave inverters. So according to the output waveform, it can be classified as a square wave, modified sine wave and sine wave inverters. Now according to the types of load, it can be classified in two ways. A load may be a single phase or three phase, so it can be classified as a single phase inverter or a three phase inverter. And a single phase inverter is also classified in two ways, that is a half bridge inverter and full bridge inverter. And a three phase inverters can be classified also in two ways, that is a 120-degree mode of conduction and a 180-degree mode of conduction. In today's session, we will discuss this three-phase inverter and the mode, that is a 180-degree mode of conduction. So in this today's session, we will discuss this three-phase inverters. So that is the classification of the inverters. Let us start with the three-phase inverters. Okay. That is a circuit diagram for a three-phase inverters. In this circuit diagram, you can see that is the input DC supply and that is the output A, output B and output C. That means R phase, Y phase and B phase. These three phases we can get at the output. So that is the input and outputs. For obtaining a three-phase AC supply from a given DC batteries, we will use a 6 thyristor. Here we can use thyristor at that means HCR, silicon control rectifier, that is Q1, Q2, Q3, Q4, Q5 and Q6. So here the power semiconductor device is HCR. So here we can use a 6 thyristor and 6 diode D1 to D6. Okay, so this 6 power semiconductor device and 6 diode are used. These diodes are feedback diodes. Diode can be classified according to the application. It can be a rectifier diode, that is a normal PN junction diode that can be used to convert AC signal into a DC signal. And second, that is a freewheeling diode. We already know that a freewheeling diode is always connected across the inductive load. Okay, and it will release the energy through the diode, that is a freewheeling portion. And here we can use, that is a diode, that is a feedback diode. Feedback diode is always connected across the power semiconductor device. So here we can connect this diode across the HCR, and feedback diode is used in inverter. That means it can be used in DC to AC converters. It can be used in DC to AC converter. Inverter means what? It converts a DC supply into AC supply. So feedback diode is used in DC to AC converter across a power semiconductor device to return back the stored energy to the DC supply. Feedback diode function is what? To return back the stored energy to the DC supply. Okay, so that is a feedback diode and freewheeling diode and rectifier diode. Now here load will be connected across A, B and C. A load may be a resistive or inductive in nature, and it can be connected in star or delta configuration. So here we cannot connect a load here, but it can be connected like a star configuration or delta configuration. If we have to see this in a simple manner, so let us see with the load connected. So here you can see in the circuit, here we can connect the load across A, B in C. Okay, A, B and C. Here we can connect the load as a resistive load in star connect configuration. Okay, so load may be connected in this manner. So that is figure is only for understanding. We have basic, our main figure is this. Okay, okay, now the switches are, these switches are turn on and off at regular interval of 6 interval. The sequence of on and off is programmed to obtain a three-phase voltage. If we have to get a three-phase voltage, then we have to give the gate driving signal. We already know that HCR having a 3 terminal, that is anode, cathode and that is a third terminal, that is a gate terminal. So in the third terminal we have to give the control signals. Okay, so depending on the types of control signals, applied to the thyristor, it can be three-phase inverters can be obtained in a two mode of operation. It can be a 180-degree mode of conduction and 120-degree mode of conduction. In 180-degree mode of conduction, each thyristor is remains on for 0 to 180-degree mode, and in 120-degree mode of conduction, each thyristor is remains to on for 120-degree mode of conduction. Means what? In 180-degree, a thyristor remains on for 0 to 180-degree, and in 120-degree, a thyristor remains to on for 0 to 120-degree. Okay. In three-phase inverter, at any given instant of time, 3 thyristor will be conduct simultaneously. In this circuit diagram, we have seen 6 thyristor, but in every interval, it have a 6 interval. So in the every interval, a 3 thyristor is remains to be on in every interval. Okay. Now in 180-degree mode of conduction, after every 60 degree, one of the conducting thyristor is turn off and the other thyristor comes into the conduction. Means after every 60 degree, one of the thyristor is turn on and another thyristor is turn off. We have seen this in the waveforms. Okay. In today's session, we will study a 180-degree mode of conduction. So let us start with 180-degree mode of conduction. In the 180-degree mode of conduction, we have to draw the gate driving waveforms. So we have to draw the gate driving waveforms. So circuit operate in 6 steps. Each step is 60 degrees. So we have draw the waveform like in this way. Each step is a 60 degrees. We have drawn 0, 60, 120, 180, 240, 300 and 360. Means we have used 0 to 360, means a wall cycle, 0 to 2 pi. Okay, in the wall cycle we have drawn the waveforms. Okay, each thyristor is operate after every 60 degree and remains on for 180 degree, because this is a 180 degree mode of conduction. Now starting with a thyristor Q1, it is fired at alpha is equal to 0 and conduct still at alpha is equal to 180 degrees. You can see it is on for 0 degree and remains on for alpha is equal to 180 degrees. Now when Q1 is on, Q2 will be fired at alpha is equal to 60 degree and remains on for 240 degrees. You can see alpha is equal to 60 degree, it can be on and it can be on for 240 degrees. So here this portion is 180 degree, it can be remains on for 180 degrees. Okay, because of 180 degree mode of conduction. Now Q3, similarly Q3 can be on for alpha is equal to 120 degrees mode of conduction. So you can see then Q4 will be on for alpha is equal to 180 degree and it can be remains on for 360 degrees. So that is a Q4, and Q4 then Q5 is on for alpha is equal to 240 degrees and Q6 is on for alpha is equal to 300 degrees. Here the sequence is continue for another cycles for 360. After 360 it can be continue for this. Okay, we have only seen for one cycle. Okay, now here that is a gate driving waveform for Q1 to Q6. Okay, in this waveform you can see here we have seen that is a mode 1 0 to 60 degrees, then mode 2 60 to 120, 180, 240, 300 and 360. So in the first mode, that is a 0 to 60 degree mode of conduction, you can see in this session the Q1 is on, Q5 is on and Q6 is on in 0 to 60 degrees mode of conduction. So we can say that in the mode 1 thyristor Q1, Q5 and Q6 is on. So thyristor 1, 5 and 6 is on in this mode of conduction. Okay. Now in second mode you can see Q1 on, Q2 on and Q6 on. So we can say that in this mode 1, 2 and 6 is on. Similarly in the third mode, that is 120 to 180 degrees, Q1, Q2 and Q3 is on, 1, 2, 3 on. In the fourth mode 4, 2 and 3 is on. In the fifth mode thyristor 4, 5 and 3 is on. In the last mode, that is a mode 6, 4, 5 and 6 is on. So that is a sequence pattern. That means step 1, step 2, step 3 and step 4 and step 5 and step 6. That means a thyristor having a 3-phase inverter having a 6 step. Each step having it in every step you can see a 3 power semiconductor device is on, means 3 thyristor is on in every interval. Okay, simultaneously. Okay, not a same, but it can be on like simultaneously. So we can say that that is a mode 1, that is a mode 2 that is a mode 3, that is a mode 4, that is mode 5, and that is a mode 6. So it having a 6 step. So the pattern is repeat for the further cycles. We have only discussed the 6 modes. Okay. So it is also called as a 6-step inverter. Why 6-step? Because it having a 6-step. So in this 6-step, so it is also called as a 6-mode inverter or a 6-step inverter. Okay. Now we have. Okay. The next topic that we will discuss in our next lecture. Okay. Thank you very much.